Hello everyone, in this video what we're going to be doing is solving the AP Calculus BC 2009 question number 2. Okay, and the reason why I do this is probably the most infamous question, the most difficult, for good reason. We'll see why later. It's a very unique question, so let's begin. So let S be the region bounded by the graph of the polar curve r of theta equals 3 root theta sine of theta squared for 0 is less than or equal to theta, which is less than or equal to square root pi, as shown in the figure above. So, okay, so you have this is r of theta, and part A, so find the area of S. So the area is equal to 1/2 times the integral of r squared d theta. And it's a definite integral from your first angle to your second angle. So you get 1/2 times the integral of 0 to square root pi of 3 root theta sine of theta squared, all of that squared, d theta. And you get a value of about 3.53429. 53429. 3.53429. So that part was not that bad, okay? Let's move on. Part B. What is the average distance from the origin to a point on the polar curve r of theta equals 3 root theta sine theta squared for 0 is less than theta is less than square root pi? So it's an average value. So we need to do is find, well, what is the distance function? So what is the distance from the origin? Well, the distance from the origin to any point on the curve is just equal to r. Okay, that's literally what a polar curve does. This polar curve for any angle theta will give the distance from the origin. So what we need to do is 1 over square root pi minus 0, that's just square root pi, times the integral from 0 to root pi of r of theta with respect to theta. Okay, so we just need to take this integral, sine theta squared d theta. Okay, so all we need to do is take this integral. So if I were to do that in my calculator, so we have 3 root theta sine of theta squared from 0 to square root pi. So you have this, which is equal to, let's say, 1.57993. And that is our answer. That's the average distance from the origin to the polar curve in the range of those angles. Okay, so C is where we start to get to the fun stuff. There's a line through the origin with positive slope m that divides the region S into 2 regions with equal areas. Write, but do not solve, an equation involving one or more integrals whose solution gives the value of m. Okay, so this is a linear rectangular equation, y equals mx. Okay, so we want to find m, but how do we relate m to polar coordinates? So let's say we're using this point here, and we want to find the slope of this line. We know r, and we know our angle. That's all that we get from polar coordinates. Now, what if I were to drop down a perpendicular from this point to the x-axis? This would be the y-coordinate, this would be the x-coordinate. Yes? So x is y. So this point, x comma y. Right? For some x and for some y. Now, y over x, because it's going through the origin, our slope m is equal to y over x. Now, there's one other thing that is also equal to y over x. And if you look at this angle, its tangent is also equal to y over x. Okay, the opposite over the adjacent side. So m equals the tangent of theta. And that's very, very convenient because now we can express an angle in terms of n, the arctangent or the inverse tangent of m. So what we can do is write the integral 0 to arctangent of m of 1/2, gotta put that 1/2 in front, 3 root theta sine of theta squared, that's squared, d theta equals 1/2 times 1/2 times the integral from 0 to the arctangent of m of 3 root theta sine theta squared d theta. Okay, so what this expression basically means is that we want to, it's not arctangent of m over here. Oops, it's actually square root pi. That's the total area. Okay, and that is our expression. Okay, so what it basically means is that the area from here to here, from here all the way to this line, so if I were to shade in this red, from here to here, this expression has to be equal to half of the full expression. That's when you know it's divided into two regions of equal area. One region is half of the total region. Okay, so D is what threw everybody off, honestly, because D is a very unique question. So for k is greater than 0, let A of k be the area of the portion of region S that is also inside the circle R equals k cosine theta. Find the limit as k approaches infinity of A of k. So they're telling us if we have this circle, okay, if we have this circle, okay, this is our k. If we had this circle and k grew larger, so the diameter grew infinitely large, then this common area, highlight in blue, what will that start to approach as k gets larger, as the diameter of this circle grows infinitely larger? Okay, now if you want to find this area, this common area, first, you need to know what angle they intersect. If we know what angle they intersect that, then we can easily find the area of this common region, okay? We can easily find the area of this common region. Just take the area of R from here to here, and take the of our R of theta from this point to this angle, then take the area of the circle from this angle to 90 degrees, okay? Now, we want to see as k approaches, becomes infinitely large, okay? So let's see what happens at intersection angle over here, because what happens is really interesting. So if I were to write this, just solve for the intersection angle and divide by k. And this step is crucial. Otherwise, you don't really see what happens as the circle grows infinitely large. So if I were to take the limit, as k approaches infinity of this, because k is growing infinitely large, so we can just take the limit of this of this and find the intersection angle, the limit of the intersection angle. So k approaches infinity, this equals 0, regardless of what theta is, okay? Regardless of what theta is, k becomes infinitely large, so this equals 0. So we're basically left with cosine of theta approaches 0 as k approaches infinity. Okay, as k approaches infinity. And that gets you theta approaches pi over 2. Approaches pi over 2 as k approaches infinity. So what you're basically trying to do is as the circle grows infinitely large, okay, until it's so large over here, it's so large that you can easily see that this intersection angle starts to approach 90 degrees, pi over 2, okay? Pi over 2. And we just showed that mathematically. So the limit as k approaches infinity of a of k is just equal to this of the integral, the area of S from 0 to pi over 2. Pi over 2 of 3 root theta sine of theta squared. That squared d theta. Okay, and if I were to plug that into the, if I were to plug that in over here, what do we get? We get, let us work it out for a bit. You get 3.32447. And we're done. That's exactly how you solve part D. Okay, so and we're done. We basically solved the entire Fourier response section. This is our integral expression. We have all of our answers boxed in. I can officially say that we're done. Thanks for watching.